Okay, so we start with root mean square speed or VRMS. It is the square root of the mean of the squares of all the speeds of all molecules. It can be derived by calculating the mean square speed, which is given by V square average is 0 to n square. Like V average we calculated, we have to calculate the V square average. So 0 to infinity V square FV dV, and if we substitute the value of FV like before, we end up with this expression. And if we do the integration, we get V square average is root over 3 RT by M. So this is the value of root mean square speed or VRMS. So the root mean square speed is the square root of this mean speeds, mean square speed. Okay, so VRMS is root over V square average. So you get root over 3 RT by M. So if we see, okay, so what we discuss now, so we got the VMP is most probably is root over 2 RT by M, and V average is root over 8 RT by pi M. The value of pi is 3.14. So we get roughly a little more than 6 to root over 2.6 RT by M, and this one we get root over 3 RT by M. So V RMS value is the highest among these three, and if we take the relationship, if we take the ratio of them, we get VMP is to V average times V RMS, we get 1 is to 1.128 is to 1.224. Now if we will see the effect of temperature on the distribution of speeds. So as I mentioned, okay, so if we increase the temperature, you get see the fraction of molecules with very high velocity is like this. Okay, this is the broader curve becomes broader here, and when temperature is very small, okay, so you get very small number of particles with very high speed, and most of the particles are having very slow speed. But as we increase the temperature, okay, the curve becomes broader, and you get the maximum speed, number of molecules having high speed, very high speed is very high here. So as the temperature increases, the average kinetic energy of gas molecules increases. This causes the distribution curve to shift towards the higher molecular speed. The peak of the distribution curve, which corresponds to the most probable speed, shifts to the right, indicating higher speed. So okay, you can see that it shifts to the right is a higher speed. Okay, so large number of molecules, they will have very high speed. The height of the peak lowers and the curve broadens with increasing temperature, which means that wider range of molecular speeds. So we get very wide range of molecular speeds here. Conversely, at lower temperature, the distribution curve is sharply peaked and concentrated at lower speed. That I just discussed. Next, we discuss collision in gas, and we will calculate collision diameter. The kinetic theory of gases treats molecule as point masses. When two such molecules approach each other, a point is reached at which they cannot come closer beyond a certain distance, like this. So one particle is this, another particle is this. The closest distance between the centers of two molecules taking part in collision is called the collision diameter. So this is the closest distance. Okay, so this is the collision diameter. It is denoted by d or sigma. So we are denoting it here by sigma. This is collision diameter. So what is collision frequency? So total number of collisions taking place in a unit volume per second is called the collision frequency Z. For binary collision, Z is 1 by root over 2 pi v d square n square, where v is the average velocity, d is molecular diameter, and n is the number of molecules per unit volume. It is not total number of molecules or number of moles, it is number of molecules per unit volume. At a particular temperature, Z is proportional to P square. At a particular pressure, Z is proportional to 1 by T to the 3 by 2. So higher the pressure, higher will be the value of Z. Higher the temperature, lower will be the value of Z. Then we discuss a mean free path. So from the postulates of the kinetic theory, the molecules of a gas are in random motion and they collide with each other. Between two successive collisions, a molecule moves along a straight line with an uniform velocity. This path is called mean free path. Consider a system of molecules with diameter d and n is the number of molecules per unit volume. So this is the schematic diagram. Okay, so it shows that collision cylinder swept by molecules. Okay, molecules whose centers are within the cylinder would undergo collision. So centers are within the cylinder, they only undergo collision. And d is the total diameter. If a molecule moves with a average speed v and time t, then the distance travelled by the molecule is vt. In time t, the molecules move in an imaginary cylinder of volume pi d square times vt. So here d is the radius of this cylinder. If the molecule colloid with any molecule whose center is within this cylinder, then number of collision is number of molecules in the volume is pi d square v times t times n. So mean free path is nothing but distance travelled by number of collision. So lambda, if we call mean free path lambda, is vt, distance travel is vt, and the number of collision is pi d square vt times n, because the molecule moves in imaginary cylinder volume v and we have n number of particles, so we multiply it by n. So we get 1 by pi d square times n. Here we have only considered that one molecule is moving at a time, which is not exactly the true scenario. In actual practice, all the molecules are in random motion. So the average velocity of a molecule with respect to others need to be considered. So the expression for mean free path will be lambda is 1 by root over 2 pi d square times n. Now what is a perfect gas? A gas that obeys the ideal gas equation, that is Pv equals to nRT, that incorporates Boyle's law, Charles' law and Gay-Lussac's law, is called perfect gas or ideal gas. In real life, no gas is perfect. So deviation from the ideal behavior and compressibility factor. So an ideal gas is the one that obeys the ideal gas equation that just mentioned, Pv is nRT at all pressures and temperatures. However, no gas is ideal. They approach perfection as the temperature gets further from their boiling points. Thus, the gases H2, N2 and CO2 which fail to obey the ideal gas equation and are termed as non-ideal or real gases. The extent to which a real gas departs from ideal behavior may be depicted in terms of a function called compressibility factor or denoted by Z. For a real gas, PV is not equal to nRT. So let us assume for a real gas PV is Z times nRT, where Z is the compressibility factor. So the value of Z is PV by nRT. When the value of Z is 1, then we can say that the gas is ideal gas. But for real gas, Z is not equals to 1 because PV is not equals to nRT. Let's assume the volume of an n mole of ideal gas at temperature T and pressure P is V1 and the volume of n moles of real gas at the same temperature and pressure is V. So for an ideal gas, Z is 1, so we get 1 is PVI by nRT here from there. So we get nRT is PVI. Now putting the value of nRT in equation 11, okay, so here the equation 11 is not 11, is equation 13 we need to use here. Okay, so we get, this is not 11, this is 13 equation 13, we get Z is PV by PVI, so V by VI. So when V equals to VI, we get Z equals to 1, and if V is less than VI, if V is less than, value of Z is less than 1, and if V is greater than VI, value of Z is greater than 1. So what we get? We get that Z is the volume of n mole of real gas at temperature T and pressure P, and volume of n mole of ideal gas, means the same gas when they behave ideal gas at temperature T and pressure P. Case 1, when V is Vi, then Z is 1, it indicates that the real gas behaves like ideal gas. For real gas, it happens at Boyle's temperature. But when V is greater than Vi, then Z is greater than what? It indicates the real gas have higher PV value and less compressible than the perfect gas. Repulsive forces are now more dominant. The gases are deviated from ideal behavior, and this type of deviation is called positive deviation. So when value of z is greater than 1, we say this is positive deviation, and then their repulsive forces dominate. When V is less than Vi, then Z is less than 1, it indicates that the real gases have a lower PV value and are more compressible than the perfect gas. So attractive forces are dominating here, are now more dominating, and the gas is deviated from ideal behavior, and this type of deviation is called negative deviation. So here we have plotted Z versus P pressure. So we will see effect of pressure on Z. At very low pressure, all gases shown here have value Z equals to 1. So if we consider this region where all gases, they have the value Z equals to 1. So all gases behave nearly perfectly at very low pressure. At high pressure, all gases give or show Z greater than 1. You see, value of Z at high pressure, all value of Z is greater than 1. It signifies that they have a higher molar volume than a perfect gas, and at intermediate pressure, most gases have Z less than 1. So for intermediate pressure here, except hydrogen, you see the value of Z are negative here for all gases, indicating they have lower molar volume than the perfect gas. Now we see that effect of temperature on compressibility factor. So from this plot, it is very clear that at low temperature, a gas deviates from ideal behavior, and at high temperature, the gas tends to become ideal. You see, at low temperature here, value is less than 1, but as temperature increases here, okay, it's very close to 1 we are getting here. So as we just discussed, so not all gas molecules are ideal gas molecules. So most of the gas molecules, they behave real, they are real gas molecules. So and PV equals to nRT and does not, we cannot apply for those gas molecules. So here comes the real gas equation state. First is van der Waals gas equation of state. So by doing volume correction, because we considered in kinetic gas theory of gases that gas molecules or particles are point mass, so they do not have any volume. So by doing the volume correction, so we need to now incorporate the volume of each particle. And pressure correction, J.D. van der Waals in 1873 gave an equation that depicts the real gas. So van der Waals equation for n mole of real gas is formulated as like this. So P plus n square A by V square, V minus Nb equals to nRT, where P is the observed pressure, B is the volume. Okay, so B is 4 times 4 by 3 pi r cube times Avogadro number for 1 mole. R is universal gas constant like before, T is temperature, V is the volume occupied by 1 mole of gas, and A is constant due to pressure correction. So A, this term comes due to pressure correction, and there B term comes due to volume corrections. So A and B are often called van der Waals coefficient. Now let's see how we can apply this one for van der Waals equation. At low pressure, volume is sufficiently large, and therefore B can be neglected in comparison to V. So here you see at low pressure, volume is quite large. So V minus Nb, we can write simply V, because the value of V is quite higher, much higher than Nb. So we get P plus A by V square times V equals to RT for 1 mole. So we get PV is RT minus A by V, or PV by RT we get 1 minus A by RTV. So PV by RT is Z, so thus at low pressure ZD is less than 1, that we have already seen here. At low pressure here ZD is less than 1. So as pressure increases, means V decreases, the term A by RTV increases, consequently Z decreases with increasing. Now at high pressure, P is high and V will be very small, so that B cannot be neglected, but A by V square term can be neglected in comparison to P. So this is the expression. So now we can neglect this term at higher pressure, because the value of P is quite much higher than this term, but at higher pressure volume is small, so we cannot neglect N by Nb term. Okay, so at higher pressure, we get P times V minus B equals to RT again for n equals to 1 or 1 for 1 mole of gas. So, we get PV equals to RT plus PV. So, PV by RT is 1 plus PV by RT. So, thus Z will be greater than 1 and increases as pressure increases. You can see as pressure increases here, the value, this is the Z value, it is greater than 1. At high temperature and low pressure, if temperature is high, V is very large and therefore B as well as A by V square can be neglected. So, equation 13 becomes will be reduced to ideal gas equation. So, at high temperature and low pressure value, okay, so we can actually neglect both the correction terms A and B here, so A and B here, so we can actually get ideal gas equation. So, ideal gas equation, real gas molecules, they behave ideally at high temperature and low pressure value. Then we consider liquefaction of gases. So, gas molecules can be liquefied by increasing pressure or decreasing temperature, or by both if we increase pressure as well as decrease temperatures. So, if we plot pressure versus volume, we get this kind of curve, and this is the isotherm for CO2 at different temperature. So, the above figure gives us an idea about critical temperature, critical pressure and critical volume. So, what is critical temperature? Critical temperature is the temperature above which a gas cannot be liquefied under high the pressure, however high the pressure is. So, however high the pressure is, you cannot liquefy the gas above certain temperature. You can see the value of Tc here. So, this is the value of Tc here, okay. 30.98 is the value of Tc. So, what is the critical pressure? Critical pressure is the minimum amount of pressure that is required to liquefy the gas at the critical temperature. So, this is the critical temperature curve. So, 30.98 here, because so this is the minimum pressure is required. So, 73 is the value of pressure here. Okay, so this is the minimum amount of pressure is required. So, this is the value of Pc here. And critical volume is the volume occupied by 1 mole of gas at critical temperature and pressure. When P equals to Pc and T equals to Tc, the volume occupied by 1 mole of gas is known as critical volume. So, derivation. At critical temperature, the curve that has a flat inflection. From the properties of curve, we know that the inflection of this type only occurs when the first and second derivatives are 0. Now, equation 15 here, this one, okay, so can be written as P by RT by V minus B minus A by, this for Vm is the molar volume of 1 mole of gas. So, V by N gives you, V by small n gives you the molar volume. So, we get the value of P here. So, at critical point, so both first derivative and second derivative of pressure with respect to volume are 0. So, if we do it, so we get dP by dVm gives you this value, and d2P by d2Em dVm2 gives this 0. So, if we solve equation 17 and 18, we get Vc is 3V. So, the critical volume is 3 times the volume V factor, volume correction factor. Pc is A by 27B square and Tc is 8A by 27Br. So, this is how we get the value of Pc, Vc and Tc. So, now we discuss a reduced equation of state. Reduced means there is no unit here, okay. An equation which expresses the relation between the pressure, volume and temperature of a gas is called the equation of state or the characteristic equation. If we introduce dimensionless, so there is no dimension in pressure, volume or temperature. Dimensionless reduced variables of gas by dividing the actual variables by the corresponding critical constant. So, pressure, if we divided by critical pressure Pc, we get reduced pressure pi. Similarly, volume V, if we divided by critical volume, we get reduced volume phi. And temperature, if we divide it by reduced temperature, we get reduced temperature theta. Or critical temperature, if we divide by critical temperature, we get reduced temperature theta. So, from there we get P is pi times Pc, V is phi times Vc and T is theta times Tc. Now, if we put these values in the Van der Waals gas equation, now in the Van der Waals gas equation set, what we have? P, so instead of P we write pi times Pc, then A by V square, so A by, instead of V we write phi times Vc, we get this one. and then V minus NB, so you get phi times BC minus B, so you get this, and RT instead of T we write theta times TC. So this is now if we substitute the value of PC, VC and TC, so we got the value of PC, VC and TC here. So if we substitute those values PC, VC and TC in equation 19, so we get this expression, equation 20, and if we solve the equation 20, we get this expression. So this equation is called reduced equation of state. Here pi, phi, theta, they do not have any dimension. These are all dimensionless quantities, and pi is known as reduced pressure, phi is reduced volume, and theta is reduced temperature. So now we discussed intermolecular forces. The forces of attraction and reduction between attraction and repulsion between the interacting particles or atoms are called intermolecular forces. Intermolecular forces, such forces exist in all state of matter and responsible for structural features and physical properties of matter. Intermolecular forces arise due to the following reasons: dispersion force or London forces, dipole-dipole forces, then dipole-induced dipole forces, and hydrogen bonding. Dispersion force or London forces is like dispersion forces or London forces arise due to instantaneous dipole generated in one atom or molecule. This instantaneous dipole induces the dipole in another atom or molecule. This temporary dipole generated in two atoms attracts each other. These forces are always attractive, and the interaction energy is proportional to 1 by r to the 6, where r is the distance between two particles. So dispersion forces or London forces, these are instantaneous dipole moment has to be created, and it's proportional to 1 by r to the 6. However, these forces are very weak, and the strength of the forces depends on three factors mainly: size of the molecule, number of electrons present in the molecule, and molecular structure. So this is the schematic diagram of dispersion force. So you see these are two atomic sites. So this is the nucleus, this is the nucleus, right, of the atomic sites, and the electrons are moving around this nucleus. Now due to the presence of this nucleus, the electrons of these atoms, okay, so they actually or due to the presence of this nucleus, the electrons of this atom, they orient like this. So it creates some delta positive and delta negative charges here. Okay, so some transient dipole moments are created here. You can see first the transition dipole moment here creating, and then because of this the transition dipole moment is also created here. So the interaction between these two particles arise from this transient dipole moments. Then dipole-dipole forces, this type of forces arise when two molecules have permanent electric dipole, that is polar molecules. A polar molecule has separate centers for positive and negative charges, and the ends of the dipoles possess partial charges, which is denoted by delta. So here you can see that HCl, so H has partial positive charge and Cl is partial negative charge. Here also H is a partial positive charge and this is partial negative, and there is attraction between this delta plus and delta minus, delta plus of H and delta minus of Cl. Greater the dipole moment of the molecules, greater the forces of attraction. These interactions are stronger than the London forces but weaker than ion-ion interactions because only partial charges are involved. Dipole-dipole interactions energy between stationary polar molecule is proportional to 1 by r to the 3, but between rotating molecule is proportional to 1 by r to the 6. So depending on whether molecules are rotating or not, the interaction forces, they vary actually. So when the dipoles are stationary, is proportional to 1 by r to the 3, but when they are rotating, it's proportional to 1 by r to the 6. Then dipole-induced dipole forces, they are type of forces operate in between a polar and a non-polar molecule. When a non-polar molecule come into neighborhood of polar molecule, an induced dipole appears on these non-polar molecules. because of electron cloud of non-polar molecule gets deformed due to the electric field of polar molecule. You see, this is the non-polar molecule, this is the permanent molecule having permanent dipole moment. So because of this, there is a induced dipole creating on this non-polar molecule. Okay. So this is your dipole induced dipole forces. The interaction energy of dipole induced dipole is proportional to 1 by r to the 6 and depends on two factors: the dipole moment of the polar molecule and the polarizability of the non-polar molecule. Molecules or atoms with larger size have more tendency to get polarized. Then hydrogen bond. Hydrogen bond is a special case of dipole interactions like here. So we see the water molecules. Hydrogen atoms in water molecules are delta positively charged, and then hydrogen oxygen atom is delta negatively charged. And then this delta negative charge oxygen attracts the delta positive charge of hydrogen of another water molecules. So they form kind of bond. This is called a hydrogen bond. When a hydrogen is bound to a highly electronegative atom such as fluorine, oxygen or nitrogen, the hydrogen forms a weak bond with the electronegative atom of other molecule. This weak bond is called hydrogen bond. The energy of the hydrogen bond is around 10 to 100 kilojoule per mole.